combustion performance audit, what it is, why it's useful. My name is Tom Zhang with Optimus Solutions. I am the senior engineer. I have a co-host. It's Sarah Ballou, key account specialist. Why don't you say hi, Sarah?
Hi, everybody. Hope everybody's doing well.
And I have Kevin Pilson, who we will show him later. We'll introduce him. We have a special demo for you towards the end of the presentation. So before we get started, I would like everybody to be able to see our webcams. It will be important later on. That way, we have some things we would like to show you guys. Other than that, if you guys have any questions, there's a question box that you can ask the questions, or if you guys have issues connecting in that sense, there is emails that you can reach back out to try to help with any technical difficulties. We have staff on the background that can help get any of those technical logistical questions answered. So what is a combustion performance audit? So before we do that, why even perform something like that? Why even look at your combustion? Why even look at your performance? Okay. And most rotary processes, whether it's a rotary kiln, a rotary dryer, a rotary calciner, heat is going to be the heart of your process. You typically need to increase the temperature to do something chemically or to do something like remove moisture. Excuse me. So the combustion system is typically the heart of all most, if not all, rotary processes. And in terms of moving into that step, one of the things is to know the baseline. If you know the combustion performance of that particular piece of equipment, you typically will know details on what to do next. And one of the things we will do at the combustion performance audit is we will have additions to just basic tune-ups. So a lot of what we could do to help are things like fuel savings, production, emissions, and quality. These things are all specific metrics for you guys and your particular processes. We are not the expert of your process. You guys, the guys that run the equipment 24/7, 365 are the experts in your process. For us, we are the experts in rotary equipment. We have a lot of breadth, looking across many, many different units so that we can cross-compare, whereas you guys have a lot of depth in knowing details in that one specific unit. So that's where between you guys and Optimus, we can get a very good compatible understanding of overall. So before we do a combustion performance audit, typically we'll get an inquiry. I think Sarah knows we should try to get a conference call going. So if Sarah, you would like to talk a little bit about how we would set up the conference call?
Sure. So typically if somebody calls me and has a need, what I do is just try to get a little bit of background of, what the concerns are and what the problems are that the customer's been experiencing, and then try and schedule a time that works for Tom or one of our other engineers and myself to be on the phone with you and your team to be able to walk through that and help understand.
Right, because the most important is normally why what is the problem? Because if we don't know the problem, we don't know what to do to either further understand the problem or diagnose the problem. And then ultimately, by the end of the day, after you have a problem, you would like to know a solution. So before we even start a combustion performance audit, it is actually critical to know what type of equipment you have. It is important to know what a calciner is. Indirect fire or an indirect fired kiln is the other definition for a calciner. A rotary kiln, these are your standard 10 to 20 feet by 200 to 400 feet long large units with refractory, or your rotary dryers, which are, say, typically 8 foot by 50, maybe 70 feet, 10 feet in diameter. So each of the units have its own particular ways heat transfer. So remember in the last slide, I talked about how the combustion is the heart of the process. Well, what we all kind of know now is that each of the units have its own way the heat transfers. The way the heat transfers actually dictate the combustion process. So your unit and the problems determines the approach we take for the combustion performance audit. So for a calciner, it may be one thing. For a kiln, it may be another. For the dryer, maybe another, right? So before we do that, I like to have Sarah or both of us schedule a conference call so that we understand what your goals are, what the expectation is, and what the problem is. What I've learned now is if you understand the underlying root cause, the actual solution is relatively straightforward. Hey, this burner has exceeded its limits. The solution is replace it with a higher capacity burner. So the actual solutions are typically straightforward in the sense that it costs capital and time, or money and time. But in terms of diagnosing the problem or where it comes from, that's not always so straightforward. And as you guys know, there's lots of experts, there's lots of opinions. One of the things that we always work through is how do we make it data-driven? How do we have the numbers so that it makes sense? We can communicate that, okay, this is what we would consider good. This is what we would consider not good. This is something we can calculate. We can show that it's factual data. This is something that we say, hey, this is a rule of thumb we follow. These types of thought process, approaches, and ultimately part of our culture here is that if we don't understand it, if we can't define it, then we will work to understand and define it. We will work to make it more data-driven and more numbers-based so that when you guys ultimately have the solution, it's very, very obvious. Okay, so I'm going to talk about the next three. Next three things are what are approaches for the calciner, what are approaches for the kiln, what are approaches for the dryer. Okay, so here's the interesting with the calciner. A rotary calciner is a tube where you heat the outside of it. Okay, typically it's the flames directly on the shell, or it is really hot. It is a very hot air, hot gases that heat the shell. So if you're trying to heat the shell, typically most of the groups that we work with, the process engineers or the production team, they know what temperature they want. So the way rotor calciners work is it's in temperature zones. So let's say you have 3 zones. One zone is 800 degrees. One zone is 1200 degrees. The last zone is 1500 degrees. Okay, whatever that temperature is, our goal when I hear calciner or when Sarah hears calciner is, okay, calciner, what are the temperature targets that you guys want? Because if you know that, then what we do is we go in and try to get that temperature. So what you guys see on the right is the customer had a lot of complaints on, hey, we would like to get it closer to 800 degrees. The range that we see there is from 375 to 400 degrees up to 1,000 degrees. So, and this is Kevin doing the work. After Kevin was on site, he was able to go from 600 degrees to 900 degrees. So we reduced that variance from 600 degrees to 300 degrees. So this is something that we can show a before and after. We can show the quality metrics, which is temperature in this case, and we go on from there. Typically, in these cases, you're trying to get a certain temperature and details from that. And typically, these have multiple burners, 9 burners, 12 burners, 6 burners. It's a lot. Okay. Let's see. Anything else I'm missing, Sarah?
Why is it important to have such? I was going to ask, why is it important to have such a tight temperature tolerance, I guess, amongst all the burners on a calciner?
So the tighter it is, the more consistent the temperature from the shell to the material. So if your material needs to see, so let's say the customer wants the temperature to be 800 degrees on the shell. Your chemical change, your chemical, the cooking temperature of it may be 600 degrees. So if we get it at 800 degrees, by the time the heat gets to the shell and gets to the material, it'll be good enough to do what the customer wants, which is a chemical reaction or some part of the process they want. If the temperature range is very high, so let's say you got 400 degrees. Well, the issue with the 400 degrees now is now you've cooled it down to where now if it's 400 degrees and now it's say 200 degrees internally, you're not going to do anything. Or let's say it's 1,000 degrees and you go and it's too hot. Now the issue is going to be you may have done something detrimental to the process. So the more consistent we can get and the better the customer has control of their process. Okay?
So
second one,
if Kevin goes
go
on site, oh, sorry, I was going to say if Kevin goes on site and he adjusts those temperatures to where it's tight where the customer wants it, how difficult is it going to be for them to keep it in that range?
So when Kevin goes on site, part of his job is to work and look at the BMS system, the burner management system, take a look at the valves, take a look at those things. So it depends on the process. It could be as simple as once he sets it, all the customer has to do is just click the on button and purge it the way they follow their normal process, and the settings are already there. Or he'll find out that, hey, I'm trying to tune it. I'm trying to get it up to this temperature, but it's too, the variance is too high or something's damaged. So then he would recommend, hey, I need you to go ahead and change this valve, change this component. So then the customer's back up to normal. Cool? So the next thing is dryers. I think some of our attendees are dryer guys. So on dryers, the main thing that we want to do is look at your combustion itself. Look at, and this is where we do a combustion analysis. So the way I break up the dryers is I want to do a combustion analysis. So this takes a look at your O2 percentage, your CO parts per million, even your NOx parts per million. If that is something that our burner specialists or combustion specialists can change while on site, they would have the conversation with the customer. We would all have a brief conference call after the first analysis and go, hey, their CO is high. And what we'll do is we'll actually show a demo of that. Your CO is high. You need to decrease that. And here's what we're going to try to do. And then once we get that down, then we take some measurements and some rough details and try to perform a heat mass balance. What you see on the right is a pretty typical dryer heat mass balance energy breakdown. So what's interesting here is the gray is water latent heat and the orange is water sensible heat. Most of your dryer should be doing that, okay? Water latent heat is the boiling or the evaporation of water after it exceeds 212 degrees Fahrenheit. And then water sensible is the energy it takes to heat it up to that point. So normally on a dryer, you should see at least 40 to 60% energy usage for the water. At the same time, this is where we can take a look at that and go, okay, let's say you have an X percent of water, 10%. And let's say there's a way you can decrease the water in the land or in the feed pile before it enters the dryer, and you can decrease it by 1%. So 10% to 9%. We can run through a scenario and go, okay, how much does it cost you on yours? And typically now it's natural gas. $2, let's say $3 per million BTUs. We can then take that percentage of water. We can take the energy it takes to understand that water and show the dollars it would take if you reduce that water on your fuel savings, and on the other side of it, increase the the production rate that you have. So one of the things I've been working on now is how can I incorporate a financial model into it? Because end of the day, doing these things, yeah, it's great to know where you're at, but end of the day, it's, okay, am I at where I'm at? Am I the best that I can be? Or can I use the data that you see on the right on where I can decrease water, where I can improve that detail where it's cost effective? Because if it's, hey, you know, I can invest in X amount of technology and I decrease the fuel usage in the dryer and I save $200,000 a year, and it's a $50,000 project, it's to me a no-brainer. Your ROI is in a quarter, right? So that's kind of what I would do on the dryer, because it's simpler in the sense that it's mainly focused on moisture.
So Tom, do you usually give once you go?
Yeah.
Sorry, once you go through the heat and mass balance, which is going to be shown on the report, do you also give recommendations to the customer on how they can change those things to make it more beneficial?
Yes. Typically, by the time, before we even get to the report, I like to have conversations with the customers throughout. Yes, there will be recommendations. There's certain things that I've seen now that this is where seeing different industries and different methodologies really helps us, is that if we see over here that, hey, you know, they can decrease moisture by letting it sit outside for a little bit, or they decrease moisture by putting something as simple as a roof over it and not let the pile get wet because of the rain or something like that. That's very easy. Or it's something like that you see on the green, that's the stack loss. Their temperature is so high that it's burning up the baghouse. Well, now this is where we can suggest, okay, this sounds like it's an inefficient flighting mechanism that we can help you with to add additional flights or change the amounts there. So then it decreases that temperature or improves that stack energy loss, or helps with that. So these are different things we can do. Other scenarios are, hey, we're at 200 tons, we want to go to 400 tons. Is that reasonable? It may or may not be reasonable. If it is, hey, what do you do? What do you need to do to upgrade your burner? What do you need to do to upgrade your baghouse? Do you have enough airflow to go through your system? So that's where, going back to the beginning on understanding your problem, your intent, and your goals helps us kind of customize the answer to you, because I could tell you every piece of information, but if it doesn't help you solve your problem, it's probably not going to help. So as long as I'm here and Sarah and I kind of help you work through your problem, how to solve it, what the next path or best path is, then that's very reasonable. So yes, we can do recommendations. Kilns, interestingly, is so you got dryers, you got calciners, you got kilns. So kilns, it's less on the moisture and more on the heat input. How much heat can you put in? It is more the chemical change, how to go through something like that. One of the things we do on kilns that we don't do on everything else is do shell temperatures across the board. And this is where we can kind of get a sense of the profile of the heat, okay? Because in kilns, it's all about the radiation heat transfer, the amount of heat in a kiln, or the amount of air in a kiln is actually very little compared to a dryer on a scale-to-scale basis. So you have a lot less air, therefore you have a lot more radiation heat transfer. When there's radiation heat transfer, it's all about exposure to the bed. So one of the things is we actually take a look at the flame. We try to get an understanding of the flame. We want to do shell temperatures. That gives us a sense of where the hottest zones are. We'll still take a combustion analysis, and we could still do a tune-up of the burner if needed, and we'll still do a heat mass balance. So this particular case, we took a look at the shell temps on one kiln and saw it. There's nothing that jumps out at me on that. This is more or less you get a peak on the discharge end. On one of the combustion readings, we got something like 14,000 parts per million, and you should really be under 50 or 100 or even 50, depending on where you're at. We reduced it. The customer saved like 80 grand just on tuning the burner here. So the price of doing these is relatively small. If you guys want details, go ahead and contact Sarah. Contact us. In terms of payback, we've been doing some pretty successful jobs already. Any comments on the kiln side you want to make, Sarah?
No, I will say that I've noticed that a lot of dryer customers, when they contact us, they want they're looking for a burner tune-up, and the extra information is nice to have. Whereas a lot of kiln customers are looking more on the information side, and some don't even prefer that we touch their burner. So
Right.
That's where the conference call comes into play, is to understand what you're looking for. And if you've got somebody in the plant that makes adjustments to your burner and that's not something you want us to do, that's fine. We can come in and provide the information alone.
Right. Absolutely. And just to kind of summarize some of this, we've done each. What I always like is, how can I show value? How can we show value? How can we show that when you guys invest in us and do a service like this, how we can help, and what are the metrics that we can do to show that? Calciners tend to be temperature variants. They want to get it tightened up. They want to make sure they're burning as efficiently as possible. I think that example I showed went from a 600-degree Fahrenheit span, the highest being 1,000, the lowest being about 400, to somewhere where it's 300 degrees in span. So we've reduced it by half, okay? So 900 degrees to 600 degrees, so they have a tighter bandwidth than before. Dryers, I did one where the moisture was 7.5, and it was kind of like, yeah, we sometimes get a 7.5, sometimes it's 5, and I was like, do you know, if you keep it at 5%, what the fuel savings are? And we calculated, and for one unit, it came out to roughly $250,000. And they're like, okay, so what do we do? Okay, well, you can reduce the moisture elsewhere. And then we chat strategies on what to do there. And it comes down to if we can show value. So when they do that, they now have a number that they can go after, and within a year, they'll be able to make more money. Kilns, directly reducing CO. So this one happened to be one that we did make adjustments on, and it was very, very, very bad flame, and it was not enough air, not enough pulverization of the coal in this case, and the customer has 80,000 just from a tuning of the system. So these are some of the recommendations that we've made, and these are some of the ways it's helped customers. So I want to set this up before we get going on the next piece. It's only a couple of slides. There's two metrics I want to talk about, and I want to focus on one of them more. So O2 is just, it's one of the three pieces in the combustion triangle. You need oxygen, you need heat, you need fuel. Okay, when you put a spark on it, it creates a combustion product. Oxygen is, it gives a good amount of information on where the dryer is. If I see something that's 21%, that means that it's the same as outside air. If there's more air, great. If there's less air, great, depending on your process. If I see 21% on a kiln, that's probably not good. If I see 21% on a dryer, it's probably still not good. But if I see 18, 70%, okay, that gives me some ideas. It also gives me indications on your seal performance. Second is CO. Okay, so if we see high CO, and this is from a combustion analysis, is not good, because CO means incomplete combustion. CO means you either have too much fuel for the amount of air you have, or you have too much air, or too little air for the amount of fuel you have. So both of those are things that we can do. So what we will do, and this is where I'm going to start showing online. details for some of the other guys on, and I will see how they can show up. Okay, so right now what you guys see, and I'm going to go ahead and click out of some of ours so you guys can see the screen. Sarah, I'm gonna turn yours off. I'm gonna turn mine off. Okay, so what you guys see now is a combustion chamber, really. I have Jason has the camera. He's showing. So Jason, go ahead and show Kevin. Kevin, I have you unmuted. Say hi.
Hello there. How are you?
So that's Kevin. So if you guys have any combustion issues or anything like that, Kevin is typically the guy that comes on site. So what I want to do is do a couple of scenarios. So Kevin, why don't you go ahead and turn on the burner and get going on a bad flame. So Jason, go ahead and show that we have the combustion analyzer kind of hooked up. So that's the combustion analyzer. It's hooked up to one of the, or it's going to be hooked up to one of the spots. Because it's going to be a really bad flame in terms of CO, what's going to happen is that it's going to have very, very high, well, obviously CO. The issue is if it exceeds a certain point, it'll burn out our sensors. So we want to make sure that everything stays reasonable on it. Right now, what's happening is the system is working on the purge. So I have everybody muted because it's going to be really loud. And there is a flame. I have you unmuted, Kevin. Kevin, is that right now a kind of a bad flame?
Right now, that's kind of a bit of a neutral flame. I'm going to put the probe into the stack, and I'm going to show you exactly how it changes. Jason, you want to come in here and get a picture of this? This is demonstrating the outside air of the O2 is 20%.
Right. So that is a atmospheric. So you see the CO is 0. NOx is all low, so Kevin's going to put it in and put the meter in, and you'll be able to see some of the changes already being made. Okay, so you see how O2 went down, CO went up. Okay, so now, well, this is actually kind of a bad flame. I see the CO is really high.
Right.
Okay, so this would be a high CO flame. So that means it's kind of starving, but we'll make it even more extreme than that. Let's see here. Kevin, you're going to go ahead and make smoke, right?
Yep.
Okay. So ultimately what's going to happen is the flame is going to get starved. So you see that the flame's starting to get long. When it gets long, it's looking for air. So when it's looking for air, you're going to have high CO. So this should be a case where you'll start seeing, Kevin, you'll probably want to go take a look at the CO sensor, make sure it doesn't get overloaded, but you see the smoke coming out. When you see that on the dryer or kiln or anything, you probably don't want that unless you're intent to make incomplete. So, okay, so now the sensor should be really high. It should be close to our limits. Yeah, I see 3,000, 4,000, and climbing. So now, Kevin, why don't you go ahead and make a flame that's good? So you guys also see that the O2, yeah, go ahead and pull it. You also see that the O2 is 0.6. It's really, 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 really low. And you actually see the warning sign on that. Because it's overly saturated CO monitor. So now, Kevin, go ahead and make it a good flame. So while I go and talk about some of the details. So a good flame is going to be something that has a very low CO, so you have great complete combustion. On kilns, you'll have to deal more on the NOx because the temperatures are going to be high, and those are thermal NOx. I think that's exceeding 1,200, 1,500 degrees F. So that's something we got to watch once it gets up to those temperature ranges. But on a dryer or even on a calciner, your goal is to have complete combustion, because when that happens, that gives you the most amount of heat for the input that you put in because it's complete combustion. You also saw that when it's incomplete, it started to starve the oxygen. When it started to starve the oxygen, you will see that the O2% starts to go very, very low, okay? And when that happens, like I said, the flame is starving. It wants more air, so it tends to be longer because it's looking for air. It's, yeah, I think Jason's computer went offline for a little bit. I'll keep on continuing. Once the guys finish get kind of the technical difficulty done, we can go on from there. So the way I talk about that example is this. You got a big guy. I think Sarah knows this example. You got a big guy. The flame is a big guy, okay? So he can't move, okay? If I'm going to switch it back to my webcam for a little bit while the guys work out some of those details. If you have a guy with a sandwich, right? So I'm going to unmute Sarah so we can chat a little bit on the sandwich. If you're close, if the air or the sandwiches are close, he'll eat next to him. But if you put the sandwiches further away, it's going to be harder to just grab something close to you. So he's going to have to go further down. So if you have a starved flame, the flame is going to go looking for air. You got a starved guy, he's going to go looking for food. Okay? That's kind of how, if I'm at home, I just go to the fridge. If I needed something else, then I'm just going to go to Walmart or wherever.
I prefer to have the sandwiches brought to me.
So I don't know what that is in terms of the combustion side. If you get delivery, those types of details. We'll wait a little bit to see how the guys do on a good combustion. But ultimately, just to kind of explain a good combustion, what happens is you saw that the O2 was 0.2, 0.5%. So when you have good combustion, you then on a kiln, you're in the 2 to 5% range, depending on the industry, like lightweight cement, pulp and paper, etc. On the dryers, you'll tend to be higher because there's more air in general, so you're in the maybe 10 to 15%, maybe 17, 18%. But the key there is your CO. If your CO is 1,000 or more, typically that's pretty bad. We try to make adjustments when we see something above 1,000, or we recommend you guys make an adjustment. If not, then if your CO is maybe 20 and your NOx is maybe 20 parts per million, under 50 is kind of our general rule of thumb, then that would be a good combustion. And if they get back online and be able to do that demo, great. If not, that's really the answer to that question. So I believe, let's see here. Okay, so I just got an update on what happened. The flame got so hot that it burned out the computer. It was a surface, so we probably won't be going back to that. So that is ultimately the conclusion to this set. Unfortunately, we didn't get to see the rest of it, but it's still cool to have that. Any questions, Sarah? Any things that we need to discuss that you can think of?
So if a customer decides to bring us on site to perform a combustion audit, what do they need to be prepared for? Is there anything they need to do to prep, or is there anything that they need to provide to us before we come on site?
So typically what I would like to know are just some of your production metrics, right? So on dryers, it's actually easier. They tend to be a simpler mass balance set. On kilns, one of the things I always talk about is what are the different portholes that we can use to measure the combustion analysis. And actually same with dryers on what that is. Because if we can't have access, then we're running blind typically. So typically that's in the discharge hood to or actually, depending on the counterflow or parallel flow, the exhaust gas side is typically where I would like to know the O2 and the COs. The other thing is, again, the metrics. What kind of feed rate are you running? What are some of the temperatures you have, or where the control room is, so we can do some of the recording on it. So that's something we would prep.
My only other question would be, so with the information that's being provided, it becomes more of a baseline rather than just a tune-up. So how often do you recommend that this baseline be performed?
So the simplest version of that one is, if you have a problem, it's good to go ahead and do another one, or if something changes. If nothing changes, I like to do it yearly, so every 12 months, or after you shut down and come back up, because sometimes settings change, sometimes materials change. So when something changes and you already have a baseline from us and you want to improve it, then great. Otherwise, it's a year. Oh, I see the guys are back online. I'm going to go ahead and not show our webcams again, so I can see what that is. Okay, cool. So what you got, guys? So is that a
getting ready?
Is that a good? Go ahead.
It's a start to a good flame. I'm going to be able to adjust it here once I get my meter put in the stack.
Okay.
Okay. Jason, you want to try to get a picture of that?
Okay, so that's a really good flame. So you see that the O2 is relatively low for this, but the CO is very, very low, and the NOx is under 100. Jason, can you show the flame? Okay. Well, good. I'm glad we're able to show that. And the flame itself is relatively bright. So that will be it. Okay, cool. So let's go back to us. I'm going to show me. I'm going to show Sarah. I'm going to take that off. Show my screen. Okay, cool. So overall, Sarah, any other questions? I'm glad we're able to show at least what a good flame or a good combustion looks like on the combustion analyzer.
Yeah, no, I don't think I have any other questions.
Okay, cool. Well, guys, this ultimately ends this set. If you guys got deeper questions, www.optimusps.com or optimussolutions.com. Phone number is 502-515-5822. You can email us at info@optimusps.com. We're in central business. I think the economy is starting to jump back up, but again, we're here, we're ready, we're open, we're here to help. Like I said, one of our mottos is science behind the process. We want to make everything data-driven. We want to help you guys out best we can, being as neutral in terms of the information as possible, because what you're ultimately buying is the expertise with the rotary equipment and data, so that we can all make informed decisions. So without further ado, stay safe, stay healthy, stay sane. Bye, guys.
Thank you.